Thank you very much. I'm honored to be here, and I'm going to talk about the dawn of big memory computing. But before that, I want to just give you a little bit of background on MemVerge. Most of you may not have even heard of MemVerge. But MemVerge was started in 2017. We're a Silicon Valley-based startup. And at that time, we were focused on pioneering software to do memory virtualization. So at that time, heterogeneous memory in the form of DRAM plus Intel Optane persistent memory had just started coming out onto the market. And so MemVerge worked with Intel to learn how to virtualize that memory into one larger pool, and then also to do memory tiering. And then, in addition to that, we also started pioneering what we call memory services. So one of the memory services that we've perfected that's in our cloud products today is called memory snapshots, and it's the ability to take a high-speed memory snapshot of a large pool of memory without causing a lot of overhead. And then we've also perfected technology to do what we call kind of elastic memory services, where applications or containers or whatever, their memory requirements expand and contract. So we've been perfecting that technology also on our public cloud side business. But we see all those technologies there becoming applicable to the CXL area over time. So now what I'd like to do is talk about this concept of what we call the dawn of big memory computing. And I think it's especially appropriate that I'm here in Korea, because Korea is the source of 70% of all the memory technology in the world. So congratulations. And then I also think it's especially appropriate because this is the OpenInfra OCP conference. And those two organizations are committed to bringing open computing to the whole world. And I really enjoyed the slogan from OpenInfra yesterday to basically allow anyone to do any kind of anything, anywhere. I think that's I think it's essential for us to democratize computing, to democratize things like AI, ML, and engage more people in solving the world's problems. So now what I'd like to do is just quickly recap what I mean by big memory computing. I think most of you guys know that everywhere we turn now, the data sets are getting larger and larger. This is just an example of how the number of transistors for chip designs has gone up by 2.6 million, a factor of 2.6 million since 1984. We have wafer scale designs. We have these very complicated chiplet designs. And so it's just to model and simulate all these, as you can imagine, takes an enormous amount of memory, and you guys know that. Likewise, in the life science area, since 2009, data sets have grown by a factor of 10,000. And the reason for this is that now that we've perfected DNA sequencing, and sequencing costs are now dropping down to below $200, even $100 per human DNA, we can now collect large populations, even 1 million, even more than 1 million samples of DNA, and now look for very specialized kinds of genomic variants. And so this area is exploding as part of personalized healthcare. Another area that's exploding is AI models. We talked about that just a few minutes ago, so I won't spend a lot of time on it. But basically, the size of these models has gone up by a factor of 1,000 in just the last 24 months. All these types of big data architectures today currently are using a distributed scale-out model. A lot of them are running on clouds or are in large on-prem infrastructure. But I think with the advent of Computer Express Link, we have a chance to optimize these architectures and do more scale up as well as scale out. And so CXL, just so you know some of the background of that consortium was founded in 2019. I think there was 9 founding members, and their mission was to help address this memory wall problem we just heard about a little earlier, where both capacity bound, IO bound, et cetera, and are bandwidth bound, and extend coherent memory across the PCIe fabric. So that's what CXL or Computer Express Link is all about. How do we extend coherent memory out and then also make memory actually become a first-class citizen? So there's this concept of composable memory. So last year also, the OCP organization started a subgroup under the FTI to start exploring how do we implement composable memory and make our data centers even more flexible in terms of handling different kinds of workloads. And lastly, the last logo there, that endless memory logo, that's something that MemVerge has been sponsoring now. We have something called the CXL Forum. So this afternoon's forum, I think, will be the 5th one we've hosted, and it'll be right over here in room 105. But basically, what we're doing is sponsoring a forum with multiple vendors and allow people to just to help educate the community, both in the tech sector and then also with the various applications and end users about what CXL is, and start thinking about how they can leverage this technology to transform their businesses. So I want to quickly, I'm going to give a very, very simplified summary of what CXL technology is, because I'm not sure if everybody is familiar with it, but there's 3 levels of the specification that have been developed since 2019, and it's all been mapped out. The first one is called CXL 1.1, which allows us to take a host such as right now the current AMD Genoa and the Intel Sapphire Rapids, and also the ARM Neoverse chips, all support CXL, and they currently have system memory, which I'm showing there on the left. But now we can extend the memory now over a PCIe bus, starting with Gen 5, and connect it to some sorts of expansion devices like those that Samsung and SK Hynix and other vendors are producing. And so this allows us to just immediately start addressing some of the memory-bound situations that have to do with not enough capacity or not enough bandwidth of memory within a given node. The second level of CXL specification is something called CXL 2.0, and so we're actually able, even though this is still very early stage in the industry, we're able to demonstrate some of these pooling capabilities now with some early design switches, and also with some early design multi-port memory appliances. So the idea behind the CXL 2.0 specification is to allow, for the first time, the memory to be disaggregated from the individual nodes and used in a pooled fashion among multiple hosts. So on the left side, what I'm showing is the D1 through D4 and D number sign. Those represent memory expansion cards. Maybe they're 128 gigs apiece, 256 512, but these are memory expansion cards that are using either AIC or 3.S form factor. Plugging into a switch, we can use a switch, or in some cases people have developed multi-port solutions that do not require a switch. But anyway, we're basically able to, with a single logical device implementation, map one of those expansion cards to a particular host. On the right side, we're showing what we call MLD, or multiple logical devices, where we now basically slice up the physical expansion cards into multiple logical devices, and then allocate slices of each of those devices to different hosts. So that way, with this kind of architecture, we can now scale capacity and bandwidth improvements independently for given hosts. The third level of the specification is called CXL 3.0, and that involves multi-level switching. So just like a regular network, there's going to be top of the right rack switches and leaf switches, and also the CXL specification, and besides supporting coherent memory, is also going to support things like smart NICs, which have their own memory caches. It's going to support GPUs, DPUs, any kind of new accelerator device, FPGAs, that has its own cache, and coordinate with the host nodes as far as maintaining overall coherency. So, and another exciting aspect of CXL 3.0 is that will enable hardware-enforced coherent memory sharing. So the previous slide was showing pooling. So basically with a pool, I can just take some physical layer amount of storage and assign it to one host or to another host. With sharing, multiple hosts can see the same memory pool at the same memory address range at the same time. And some of this kind of capability we can actually implement in software right now. So we actually are able to demonstrate memory sharing even right now, even though CXL 3.0 multi-level switches are still a couple of years away. And another nice feature of CXL 3.0 is this peer-to-peer capability of transferring data between one expansion card and another without having to move all the data up into the host and then back down into copy it back down into another expansion card. So this will help us in architecturally in terms of rebalancing the memory workload or doing other sorts of accelerated processes without having a bottleneck of having to transfer all data up to the host. CXL itself is a protocol, so it's going to be running right now on the transport layer is PCIe starting with Gen 5 or higher, and that's a huge advantage. As you know, the DDR bus is a parallel bus. It's very hard to scale it up, continue to scale it up. PCIe has a well-known roadmap. These kinds of roadmap hardware advances are easily attainable. And so with one lane on PCI Gen 5, you can see there, we're going to get 8 gigs a second. And so for a given PCIe generation for each server, we will be able to scale out performance and bandwidth by just adding more and more lanes. I think one of the biggest implications of CXL is it's going to enable something called memory disaggregation, excuse me. And that really is a sea change. I have enough gray hair now that I remember when fiber channel and storage area networks emerged. And basically what happened was prior to that, storage was always coupled to servers, and servers were getting fatter and fatter. And all of a sudden they started getting skinnier and skinnier, and the storage got moved into its own storage area network, which created needs to manage that, and then also allow composability of storage. I think a similar thing, to a certain extent, will happen with memory. We'll see memory become what I call a first-class citizen in the data center. It'll be disaggregated. It'll be in a pool by itself, either allocated or shared. And we will see need to develop a lot of software to manage that, because unlike the storage industry, the big difference will be coherency has to be maintained between that pool and the hosts, which we believe will continue to have a significant amount of memory. So there are some similarities, but there are some differences. And I think we're on one of the most, at the beginning of one of the most significant changes in computer architecture that we've seen in the last couple decades with this memory composability. And so that leads to this diagram where we're talking about full-blown composability across the data center. Today, on the column on the left there, you just see stacks of servers with their own private memory, basically, sitting there on the DDR bus. The next column, we're seeing CXL 1.1, basically, where we're supplementing that memory on the DRAM bus, DDR bus, with CXL memory running on a PCIe, inside a PCIe slot on that same server. And from a latency standpoint, that'll be equivalent to about 1 NUMA hop in latency difference. So pretty much applications should work pretty much as is. And then the third column shows us now introducing memory appliances and what we call JBOM, just a bunch of memory, or switches, or both, combinations of both. But now we're starting to be able to pool and share memory across a rack full of servers. And then the last column on the left, on the right, sorry, the future, I think there'll be other technologies like photonics coming out that will allow to extend the distance that we can propagate the PCIe fabric, and then also multi-layer switches and hardware-enforced coherent memory sharing. So now I'd like to turn to a problem that's near and dear to us. The hyperscalers, like, you know, if you've read anything about the CXL, hyperscalers have been talking for about a year now about the stranded memory problem. I kind of don't like that term, stranded memory problem. I like to take the reciprocal of that and say, we really have an out-of-memory problem. And I think this is one of the most common problems that we see in a data center, data-intensive workload. And what I mean by that is that the distributed applications, and they're scaled out massively, it could be 1,000 nodes or whatever, they can't predict the distribution of resource requirements, even though they've nicely partitioned everything and sharded it. And often there's skewing occurring. There's certain nodes that are overloaded at certain times and then have higher memory usages. And what happens is, once this memory usage exceeds a certain amount, they start spilling, they run out of memory and they start spilling onto a disk or SSD or whatever, and that's called memory swapping, and you see a huge degradation in performance. And even worse, there are certain platforms like Kubernetes. We're here to talk about Kubernetes also at this conference. Kubernetes is typically configured so that there is no memory swap. So basically what happens with Kubernetes, you just basically run out of memory, and then the scheduler kills that pod and moves it somewhere else. So basically, out of memory causes the pod to be killed and moved somewhere else. And that's okay if you've got a nice cloud-native microservice architecture, but a lot of people are trying to run native applications on Kubernetes, so that doesn't work quite so well. So these are the kinds of problems, I think, practical problems, I think we can solve in the very near future using CXL. And the way we'll solve it is what we call the endless memory approach with CXL. So we're going to get rid of out-of-memory errors. We're going to create a memory pool that's shown there on the left. At a steady state, there's enough memory inside each host. But when we have our own detectors that detect that we're running out of memory, then we dynamically allocate more memory from this pool to those particular hosts so they don't run out of memory, they don't get disrupted or migrated somewhere else, et cetera. And then when the memory pressure drops from those applications, because a lot of these things are transient, we can remove that memory and use it for something else. So the benefits of all that are to reduce cost and improve efficiency. So I think we'll see a rebalancing of memory between the servers and the memory pools over time. We'll also see a decrease in downtime, because I think besides using the memory pool to deal with out-of-memory problems, we'll also be using the memory pool to deal with memory chip failures, where we can dynamically replace those by drawing from the reserve memory in the pool to replace any failures within the pool or within the local hosts. And then also we can optimize memory usage. So that technology I talked about earlier about how we can monitor how applications are using more or less memory, we can apply that in this area and then use that to help optimize performance and tiering. And we'll unite all that with a unified memory management approach. So I think the other thing that's been talked about at this conference is how to build a sustainable future for clouds. And so this elasticity of memory is going to be very important, tied together with resource management to even with the CXL 3.0 spec, we're able to even hot plug memory, plug and unplug memory, turn it on, turn it off, based on workloads. And similarly, what I described earlier, where we can, what we call wave ride, the size of the memory consumption of an application, so we can dynamically change the amount of memory and then also save power and carbon that way. With respect to AI, a lot of people talk about AI, so I want to weigh in on this topic. Training the GPT-3 model required about $12 million of electricity, and this is kind of the breakdown of that electrical consumption in terms of picojoules. And So if you look at the bottom there, the bottom of this pyramid, the vast majority of electrical consumption actually has to do with inter-server communication. It's more than an order of magnitude higher than the next tier, which is chip and DRAM communication, and then lastly, actually the computation. So there's a huge amount of electricity being spent on these models, moving data around to the right node in this big distributed scale-out model. And then also, typically what happens is that you have to serialize and deserialize it, convert it into a file, then convert it back into memory, load it into memory, et cetera. So we're hoping that we can consolidate it to a certain degree, this distributed memory architecture around shared memory pools, and we've already built a prototype, which we call Project Gizmo, which stands for Global I/O-Free Shared Memory Objects. So a lot of these training programs, they run in epochs. The machine learning training process runs in epochs, and between each epoch, there's a huge amount of data being shuffled between all the different compute nodes. And you can imagine that amount of shuffling just goes up almost exponentially as it scales out more and more. So there's a lot of energy being spent there. If we can consolidate it so they're all sharing the same memory pool, then we're eliminating or reducing the shuffling that's going on during these training epochs dramatically. We can also reduce the number of memory copies, and we can also, I believe, significantly shorten the training time. And then also when it comes on the other end of the machine learning pipeline, inferencing scalability can also be accelerated by using memory-based model serving. So the key to endless memory, I think, is going to be the software stack, and we're busy members building all these different pieces. I'll be discussing this in more detail at, I think, starting at 1:30 is the CXL track, so I'll talk more about this and this shared memory object layer we call Gizmo. But basically, we'll be working with the whole industry, and then not just the hardware industry, but also the various open source communities, including Kubernetes, OpenStack, the Linux Foundation with KVM, the different open source AI and data analytics platforms to bring the benefits of CXL memory pooling, sharing, and tiering to those applications. With that, I'm basically saying we're going to solve this memory problem and get rid of out-of-memory problems across the board in our industry. And so the next steps I'd like to encourage you guys to do is, join us at 1:30. We're going to start half an hour before the other tracks, and we have a lot of content to cover. And we'll talk about more specifics on memory tiering, pooling, and sharing. And then also, if you want to join our CXL forum community, that way you'll be on a mailing list, you can get updates on what's going on in the industry, et cetera. With that, I want to thank you for your time, and hope you have a productive conference. Thank you.